Of the original 7 wonders of the ancient world, only one is still standing strong today. I'm of course referring to the Great Pyramids of Giza, which are the oldest and, by extension, longest surviving wonders still in existence. But how were they built? And more specifically, how were the Great Pyramids' multi-ton blocks lifted to such great heights? It's easy to be awestruck by the sheer size and weight of these massive structures, and even think something supernatural must have been responsible. In this video, we're going to roll up our sleeves and actually calculate the forces involved in building these pyramids, block by block. The Egyptians didn't exactly leave behind any schematics, but using some basic principles of physics and geometry, as well as the size and masses of the actual blocks used in the pyramid, we're going to backwards engineer the machine they used and determine exactly how much lifting power they needed in order to lift a 10-ton block. And if you still have doubts by the end of this video, I guess you have to go and ask the aliens for yourself how they did it. Construction on the Great Pyramid of Giza, the largest of the 3 main pyramids, began around 2575 BC and took around 27 years to complete. Built as a tomb for the pharaoh Khufu, the Great Pyramid initially stood 481 feet tall and remained the world's tallest structure for over 3,800 years. What's just as impressive as the Great Pyramid's sheer size is its massive weight, clocking in at around 6 million tons in total. It was constructed with around 2.3 million limestone blocks, with an average block weighing around 2.5 tons. Around the base of the pyramid, the blocks weigh up to 10 tons. Considering the weight of an average refrigerator is around 250 pounds, a 10 metric ton block has the same weight as around 88 refrigerators. Without the invention of heavy cranes, bulldozers, or heavy lifting machinery, these blocks are quite formidable to move and manipulate. If you lined up a group of workers, shoulder to shoulder around the base of a limestone block, with dimensions of 1 by 2.5 meters, you may be able to squeeze in 14 workers around the perimeter. And if each worker is capable of lifting up to, say, 200 pounds, then the max load this group would be able to lift is around 1.3 metric tons. Just another 8.7 to go. Also, keep in mind, in order to construct this pyramid with 2.3 million blocks over a 27-year period, this means the workers needed to lay down 1 block in the pyramid every 6 minutes for 24 hours a day for the entire 27-year period. How did they do this? Well, before we get too far, make sure to subscribe to my channel and hit that like button. And if you've already subscribed, welcome back. Okay, so logistics aside, the ability of the ancient Egyptians to lift these heavy stones was aided by a simple machine. The ancient historian Herodotus documented his observations of the Egyptians building pyramids and the simple machine they used around the 5th century BC. Leonardo da Vinci, some 2,000 years later, used this historian's descriptions to sketch a model of this machine used by the ancient Egyptians. This machine was later named the Herodotus Machine, after the famed historian. It's worth noting, this is well before the time of the fundamental laws of motion, which were, of course, established by Sir Isaac Newton in 1687. Here's a more updated take on Da Vinci's drawings of the Herodotus machine. The block to be lifted has a large wooden beam centered along its top face and secured with several wraps of heavy rope. The wooden beam is approximately 3 times the length of the block. A wooden scaffold is built around the block and centered with the block's center of mass. The wooden scaffold consists of a long vertical board in the front, which is approximately double the height of the block. Notice the 2 columns of vertical slits, just offset from the center of the board. Each slit is wide enough for those smaller wooden slats on the ground to be inserted. The entire machine is positioned in front of the desired location where the block is to be stacked. The basic operation works like this. While the block is tilted to the left, there's just enough clearance underneath the block for 2 of those wooden slats to be inserted in the column on the right. So now there's 2 slats on the right and 1 slat on the left. The block can then be pivoted around the slats on the right and rotated clockwise. But notice, this now leaves extra clearance below the block on the left column. 2 more slats can be inserted in this left column, bringing its total to 3 slats, while the right column still only has 2. The block is then pivoted around the slats on the left and rotated counterclockwise. This process then repeats. Notice, each time the block is rotated, there's a net gain of at least 1 wooden slat on the opposite column to the pivot point. As slats continue to get added below the stone block, the block is gradually raised off the ground, 1 wooden slat at a time. Once it reaches the desired height, the block can be pushed off the machine and onto the supporting block or level. Now this is a neat idea, but you can make anything look convincing with a good enough animation. What about the actual forces involved? And exactly how much weight would workers still need to lift when rotating a 10-ton block using this machine? Well, in order to be more quantitative about this, we need to get a quick crash course on levers, counterweights, and the basic physics of what's going on. If you already have a handle on these ideas, you can skip ahead to the next section where I do the calculations. But a quick refresher never hurts. As you may have guessed, the Herodotus machine is an example of a lever system. A lever system consists of a rigid rod, represented by the brown beam, and a pivot, represented here by the green triangle. The rod is free to rotate around the pivot, but if the pivot is located exactly at the center of the beam is balanced as shown here. Now, what happens if a load is added to the left-hand side of the beam? Notice, the downward force of gravity from the load is acting at some distance away from the pivot point. To quantify this, we need to introduce a quantity known as torque, often symbolized by the Greek letter tau. Torque describes how an object, such as a lever, will rotate around a fixed point, such as a pivot. When the net torque on the lever is 0, the lever will be at equilibrium and not rotate. But anytime the net torque is non-zero, the lever will rotate either clockwise or counterclockwise, depending on the sign of the net torque. To calculate torque, we need to define a couple of quantities. Let's define the distance from the pivot point to the load as r, with r being a vector pointing away from the pivot point. Then let's define the load's gravitational force acting on the lever as F sub g, which is a vector pointing down. The resulting torque is then the product of r and F. One caveat here that I'd like to mention for completeness is that torque depends on the direction of the acting force on the lever. One way to think about this: if the force was acting parallel to the lever wouldn't rotate, and the torque would be 0. But if that same force acted at some angle to the lever, the perpendicular component of the force would cause the lever to rotate, and the torque would be non-zero. Mathematically, the perpendicular component of the force can be captured using a trigonometry relationship between r, f, and the subtended angle between them. Notice, when the angle between r and f is 90 degrees, like it is in this example, sine of 90 degrees is 1, so the resultant torque is simply the product of r and f. I just wanted to highlight this nuance, as having nice angles of 90 degrees is more of an exception rather than the rule. Once you determine the magnitude of torque, you need to determine its direction. Essentially, the torque will cause either one of 2 possible rotations, either clockwise or counterclockwise. To distinguish the rotation direction, we can assign counterclockwise rotations to be positive and clockwise rotations to be negative. To figure this out, simply follow the arrow of the applied force around the pivot point, and the direction of the circle will be the same as that of the torque. You can also use the right-hand rule in determining this direction, but no one ever seems to like that. So in this example, we see that the net torque acting on the load is counterclockwise, and hence the left-hand side of the lever falls and the right-hand side of the lever rises. Not too surprising. Now, if we wanted to raise this load back up, we would need to apply an equal and opposite torque to this lever. One obvious way to achieve this is to apply a downward force on the right-hand side of the lever at the same distance r away from the pivot point. Notice, the resulting torque from this force is negative since it would cause a clockwise rotation around the pivot. This forces the net torque acting on the lever to sum to 0. Also notice, the lever is back at its equilibrium position. Again, not too surprising. However, what happens when the pivot is shifted closer to the load? For the left-hand side of the lever, the distance from the pivot has decreased, and hence, so has its torque. But the exact opposite has occurred on the right-hand side of the lever. That is, the torque due to the applied force has increased since its distance from the pivot has also increased. Since this causes the net torque on the lever to be negative, the lever will rotate clockwise, and the load rises. Notice, the strength of the applied force has not changed. A second load can be added to increase the torque on the left-hand side and bring the lever back into equilibrium. Now, if a third load is added to the left-hand side, this will overcome the torque due to the applied force, and the lever will again swing in a counterclockwise direction. Is there a clever way to bring this lever back to equilibrium without moving the pivot or increasing the applied force on the right-hand side? Well, yes. If another load is added to the right-hand side of the lever, the gravitational force of the load will increase the torque on the right-hand side. Hence, the net torque sums back to zero, and the lever rotates clockwise back to equilibrium. This weight is known as a counterweight. Notice, the same applied force used in lifting a single block is now being used to lift 3 blocks. The same applied force can actually be used to lift any arbitrary number of blocks, as long as enough counterweight is added to compensate. The use of a counterweight is a simple idea, but is the basis for lifting heavy objects in all modern machines. Now let's revisit the Herodotus machine and see exactly how much force the Egyptians needed to use to lift those heavy 10-ton blocks. To find the force needed to lift the block, we need to focus on the key elements of the Herodotus machine. The key components are essentially the 2 pivots, the block, and the wooden beam across the top of the block. We know the length of the block L, which is 2.5 meters, and the length of the wooden beam is approximately 3 times this length, or 3L. The block's center of mass is centered between the 2 pivots. We know the 2 pivots are offset from the center of mass, but the Egyptians didn't exactly leave us with a detailed schematic, so we're going to leave the distance between each pivot and the center of mass as a free variable for now, and label this with the Greek letter delta. This distance will play an important role later on, so keep this one in mind. Now we only want to rotate the block around one of the pivots, so for the sake of the analysis, let's just focus on the left pivot. We also just want to find the minimum force necessary to lift the block. Any force greater than this, and the block would simply rotate faster around the pivot. So we want to find the applied force that would bring the system into equilibrium, as pictured here. So to reframe our question, what is the minimum applied force required to bring the system into equilibrium? From our discussion before, remember, a lever system reaches equilibrium when it has a net torque of 0. So to find the applied force, we simply need to find the torque produced by each of the forces acting on the system, set the resultant net torque to 0, and then solve for F applied. Let's begin by finding the torque from each of the applied forces. It may be difficult to see at first, but the applied force on the left is located a distance of L plus L over 2 minus delta from the pivot. So the corresponding torque would be the product of this distance and the applied force, which we're trying to find. The sign of the torque is positive since this force would induce a counterclockwise rotation. The applied force on the right is a distance of L plus L over 2 plus delta from the pivot. The resultant torque from this force is positive as well since it would also induce a counterclockwise rotation. Now, if these were the only forces involved, the net torque would clearly be positive and the system would rotate counterclockwise. But this isn't the case. We next need to consider the torque from the mass of the block. Notice the mass of the block is distributed asymmetrically about the pivot. To account for this, we can consider each side's center of mass separately, and then find the resultant torque from each side. We can find exact expressions for these centers of mass later, but for now let's just label them as F sub G1 and F sub G2. For the left-hand side, the center of mass is located halfway between the pivot and the left-hand side of the block. So its distance from the pivot is 1/2 times L over 2 minus delta. Since this force would also induce counterclockwise rotations, the resultant torque is positive. This is our counterweight of this system. Now, for the right side center of mass. Notice, it's located a farther distance away from the pivot, having a distance of 1/2 times L over 2 plus delta. Another key difference is the sign. Notice, the force F sub G2 would induce a clockwise rotation around the pivot. So the sign of the torque from this force is negative. Now, we have all of our torque expressions, but before we proceed, let's do a little housekeeping. We can combine like terms in the torque expressions and clean up some of the mixed fractions. We also need to specify F sub G1 and F sub G2. The total gravitational force on the block is mg, with the mass of the block m being 10 metric tons. This needs to be distributed accordingly across both sides of the pivot. So, the left side center of mass is simply a ratio of its length to the total length of the block, multiplied by mg. Likewise, the right side center of mass is a ratio of its corresponding length to the total length of the block, also multiplied by mg. We can substitute these expressions in for F sub G1 and F sub G2 from above. Now, our only remaining unknowns are F applied and delta. To find an expression for these, we can tie everything together by summing each torque term together. The first two torque terms sum together as F applied times 3L, and the torque terms for the block sum together as mg over 8L times 8 delta L, which simplifies nicely to negative mg delta. Setting this equal to 0 for the equilibrium condition, we can then solve for F applied, which reduces to mg over 3L times delta. Now this is an interesting result because it shows the required force needed to lift the block is directly proportional to delta, which again is the pivot's distance away from the block's center of mass. To help visualize the relationship between F applied and delta, let's plot this linear relationship using the real values of the block's mass and length. As delta increases, so does the required lifting force. For instance, when the pivot is 25 centimeters from the block's center of mass, rotating the 10-ton block would be equivalent to lifting a 333 kilogram object. 333 kilograms is still quite a load, but with 5 or 6 workers on each side of the wooden beam, this is a much more achievable force to apply than 10 tons. So is that it? We're finished? Not yet. At this point, you may be asking, why wouldn't delta just be kept at 0? This brings the required applied force also to 0, and likely putting some Egyptians out of the job. Well, we need to think a little more about what this delta corresponds to. Remember, the whole point of a Herodotus machine is to rotate the block just high enough to insert wooden slats. These wooden slats are what raise the block off the ground. If delta is 0, this places the pivot at the block's center of mass, and hence, there could only be one pivot, not two. And with only one pivot, there wouldn't be any way of raising the block higher. So aside from 0, what about smaller values of delta? For instance, if we chose delta to be 3 centimeters, then the applied force to lift the block would only be 40 kilograms. Well, as the saying goes, no pain, no gain. To see what I mean, let's take a deeper look into how delta influences the operation of the Herodotus machine. When the block is rotated to one side, there's only so far the block can rotate before the bottom edge hits the ground. So there's a limit on how high the block can be raised with each rotation. With a little geometry, we can figure out exactly what determines this limit. Let's again define delta as the distance from the block's center to the pivot, and hence the distance between the two pivots is 2 delta. The net height gain h is then the distance from the pivot on the right and the block. This forms a nice right triangle. If you remember your SOHCAHTOA from trigonometry, you can relate h and 2 delta with the tangent of the angle theta formed by this triangle. Now, there's not much we can do with this relation, since we don't know what theta is. But there's a similar second triangle with the same angle theta formed by the block's bottom left corner, the bottom of the pivot, and the top of the pivot. If we find what tan theta is for this triangle, we can then use that to derive a more meaningful relationship between the height h and delta. So let's figure out what tan theta is for this second triangle. The height of this triangle is equal to the thickness of the pivot, which we'll label as A. And the hypotenuse of this triangle can then be found by subtracting delta from half the length of the block. And if you know two sides of the right triangle, you can find the third using the Pythagorean theorem. So the bottom edge's length is simply the square root of the hypotenuse squared minus a squared. We can then write the tan theta of this triangle as a over the adjacent side's length, which can be rewritten in a much more useful form by factoring out an a squared from the square root in the denominator. Now, we can substitute h over 2 delta in for tan theta in our bottom expression, and then solve for h to arrive at a final expression for h. This expression looks a little daunting, and this is the point where physicists and mathematicians would start to have disagreements. To gain a little more insight into this, we can apply some approximations. First, let's tackle this square root in the denominator. If you plug in some real reasonable values in for L, delta, and A, you'll find the first term is much larger than the second term of 1. For instance, if L is 2.5 meters, delta, let's say 50 centimeters, and A, 10 centimeters, the first term equals 56.25. So if you take the square root of 56.25 and compare it with the square root of 56.25 minus 1, you'll find these agree within 1%. So it's reasonable to approximate the square root with only the first term. By doing this drastically simplifies this expression into a much nicer one. Next, we can place a restriction on the height, or I should say, a lower limit. Remember, in order to place wooden slats under the block, The block must be raised to at least as high as the thickness of a single wooden slat. Or, in the context of our analysis, h must be greater than or equal to a. Without this condition, additional wooden slats wouldn't be able to fit underneath the block, and the Herodotus machine would not allow for the block to be raised. Now, if we solve this expression for delta, we find a relationship between L and delta. Namely, delta must be greater than or equal to L divided by 6. Or, for a 2.5 meter block, delta must be greater than or equal to 42 centimeters. So if this puts a lower bound on delta, then what does this mean for the applied force? Well, we can refer back to the plot of the applied force again. For a delta value of 42 centimeters, the Herodotus machine would require a minimum lifting force of 560 kilograms, or just over 1,200 pounds of force. Still quite a hefty load, but it still drastically beats 10 tons. The Herodotus machine, while seemingly simple in design, ultimately allowed the ancient Egyptians to lift each of the massive stones of the pyramid one block at a time. Using the physics of a lever system, we found the finely tuned pivot positions to be the crucial piece in both reducing the lifting force while enabling the machine's effective operation. Its simple design would have also enabled multiple machines to be operating in tandem during the pyramid's construction. This machine also so happens to employ the same mechanical advantage of a counterweight lever system used ubiquitously around the world today. And one final note. Oftentimes, it's the most impressive feats of humans that get diminished the most. To say aliens built the pyramids is not only dishonoring the ancient Egyptians, but cheapening the very fabric of human ingenuity and craft. They were able to build massive structures that have transcended time and history. And while we can only marvel at their engineering accomplishments, we must also marvel and not forget how far we've come since their time. I'm Dr. John, and thanks for watching. Consider subscribing to my channel and let me know what you think in the comments.